What is forecasting? When we talk about forecasting, we talk about long-term forecasting. This covers horizons that start from some years and go ahead into many decades. And importantly, for the transition to zero carbon, this need to go up to 2050. So when what we forecast is electricity demand, distributed generation, and battery storage. So why we do forecasting? We do it actually for two main reasons. The major reason is that we produce forecasts with a planning purpose. So we use the long-term forecasts of demand, generation, and storage to plan our networks. The other main reason that we do forecasting is that as DNOs, we are becoming big data organizations. So there's a lot of data from measurements from our network planning, a lot of data that we process for the forecasts, and these are forecasts that we share with our stakeholders. So these forecasts are helping local authorities to produce their decarbonization plans, for example, or our customers to make their decisions. So how can we do forecasts, long-term forecasts? There are at high level two ways to do it. One is using scenarios, and the other is using probabilistic assessments. Possibly most of us are more familiar with scenarios because they are already used by DNOs and the ESO and other network companies worldwide to, let's say, frame future uncertainties on demand and generation and use it into planning. The other way is probabilistic assessments that can be, let's say, that can have a significant computational cost. It can be more complicated approaches, but we understand they can bring us some very specific benefits that we need to take into account if we want to enhance our forecasting approaches. So a critical thing for forecasts is to understand the likelihood or understand the probabilities of potential future views of the world. Traditionally, we are using scenarios, and possibly most of you are familiar with the two axes that are used to frame uncertainties. So it can be an axis for decarbonization and level of societal change, and based on whether there is more or less of one or the other, we can use these two axes to define scenarios. Probabilistic assessments are using a different approach. So in a complete probabilistic approach, we would try to model all possible outcomes, but this comes at a computational cost. Currently, we don't assign probabilities into scenarios, but this is an area where we need to improve and try to capture these probabilities. So these probabilities, when it comes to scenarios, they are more associated with the inputs into the forecasting methodologies. So for example, when it comes to economic growth, we can use GDP forecasts from the Bank of England, and there are probabilities assigned. But for several other inputs, we cannot have that. So we need to really try to enhance our forecasting methodologies in a way that we can capture these probabilities. And when we produce a forecast, a scenario trend, we can say that it's this % of likelihood that this is, let's say, an outcome in the future. When it comes to using probabilities in scenarios, the reason for doing that is that, as we said earlier, they are used in network planning. So, for example, if we take into account the worst scenario into planning, we're going to use a least worst regret approach in planning. We're going to mitigate any risks in the future to facilitate, for example, electrification of transport or heating. If we use a central forecast, or let's say average assumptions in the forecast, it's going to be a scenario that is not the worst case, but has, let's say, more likelihood to happen in the future. So all these are ways that we are currently using to define scenarios and have a sense of probability of likelihood, let's say, of future outcomes in terms of demand or generation or battery storage. When it comes to a probabilistic assessment, the focus is to try and capture all probabilities around all factors that could affect future demand, generation, or battery storage. The existing scenario-based approaches have some gaps. Although they are a simple approach to produce forecasts, they cannot capture all probabilities. A main disadvantage is that they use two axes to frame uncertainties, and we cannot really not correlate all uncertainties around these two axes. So, for example, when it comes to the charging of electric vehicles, if we consider a decarbonization axis, we can understand if we are going to have more or less EVs in the future. But this doesn't answer the question of where, when, and how fast these electric vehicles are going to charge. EV charging is a critical area for DNOs. Our network planners need to understand, let's say, uncertainties about the future levels of EV charging at different parts of the network. Our headache is not about, let's say, plant developments for EV charging. It's more around the uncertainties. So, for example, if we want to facilitate the charging of taxis in the city center, and we know about it, we can plan our networks about that. But when it comes to understanding future behavior of users of EVs, it's something that it's not certain yet. So, for example, we don't know if they're going to charge more at home or destination, how many of them will use en route chargers, what capacities they will use, what times they will use. And these are uncertainties that can be different from region to region. So a critical thing for us to understand is, let's say, these uncertainties at a regional level. So, for example, in areas where customers have access to off-street parking, we understand that it's more likely that they're going to do overnight charging using their domestic chargers. When it comes to areas where we have significant traffic flows and service stations, we expect that en route charging is going to be, let's say, more dominant in those areas. We recognize that the current scenario framework cannot really help us to understand these uncertainties of EV charging at regional level. So this has led us to register the Reflect NIA project on EV charging. This project started on February 2019 and will be running up to March 2021. In this project, what we try to do is to use probabilistic assessments on top of the scenarios, and we do that to try and frame uncertainties on EV charging at regional level. We have 3 work packages in Reflect NIA project. We're working with Element Energy, who is our main forecasting partner in this project. In work package 1, which has finished, we've gathered and processed data that are related with EV charging. In work package 2, we are now developing and finalizing a methodology to model uncertainties on EV charging across the different regions in our network. The last work package is expected to be finished by the end of this project next March, and this is going to deliver a tool that will model these uncertainties on EV charging, and we're going to have, let's say, by the end of these projects, we're going to have a tool that will allow us have enhanced forecasts when it comes to how EV charging is affecting our networks, and we can be more able to model associated risks and costs when it comes to the different decisions in network planning to facilitate the electrification of transport. Our Reflect NIA project builds on our previous NIA projects, and more specifically it builds on Atlas NIA project and our Demand Scenarios NIA project. Atlas NIA project was running from 2015 to 2017, and was used to develop a holistic approach in forecasting. It was using scenarios and was used to produce forecasts for the whole of our grid and primary network. Our Demand Scenarios NIA project has developed a real option CBA methodology and tools that are used for the decision making in network planning. So using these tools, we can make cost assessment and risk assessments for different network interventions and flexible services. So what we are doing in Reflect NIA project is to introduce the concept of micro scenarios. Micro scenarios is a set of scenarios with associated probabilities around each core scenario. They are produced through a probabilistic assessment, and they can be used as inputs into our real option CBA tool. By doing that, we can have more insights around probabilities, risks, and likelihood of different levels of electricity demand from EV charging across different parts of the network. Our Reflect NIA project is our first attempt to use probabilistic assessments of top-of scenarios to enhance our forecasting approaches. By doing that, what we try to do is cover the gaps from using scenarios in a traditional way. So any uncertainties that cannot be captured using scenarios, we want to produce some probabilistic assessment approaches that can capture them, and by doing that, we're going to enhance the use of scenarios rather than not using scenarios and using something completely different.